Okay, problem 4 here comes from chapter 7, which dealt with interval estimates as opposed to point estimates. So in this particular problem, we're given the average zinc concentration is estimated by taking measurements from 10 different locations. You're given the sample mean and the sample standard deviation. You're told to assume that the zinc concentration is normally distributed. In order to find the right formula for the confidence interval, we looked at 3 cases, and so that may be the most difficult part here. So of determining which of the 3 cases is appropriate for this particular problem. So one case we looked at was the large sample case, where a large sample is supposed to be more than 40 observations. That doesn't apply here because there's 10 observations. The other case we looked at was if the population is normal, which it is, but then there were 2 cases. If the population standard deviation is known, or whether it's unknown. In this case, the population standard deviation is not given. What you're given is the sample standard deviation. So this is the normal population with unknown population standard deviation. So that means this, I think, was in section 7.3 of the text, if I recall correctly. So this means that for the confidence interval, we're going to rely on the T critical values instead of the Z critical values. So switching over to the whiteboard here, in this particular case, in problem 4, let me write down some of the information we have. N is equal to 10. X bar is 2.6. I think that's grams per milliliter, but I'm going to leave off the units. And 0.6 also was the standard deviation, and that was also in grams per milliliter. In part A, we're asked to find a 99% confidence interval. These confidence intervals are written as 100 times 1 minus alpha percent intervals. So for a 99% confidence interval, that implies that alpha is 0.01, okay? Because 1 minus alpha has got to be 0.99, so alpha has got to be 0.01. The confidence interval in this particular case, the formula, I think from section 7.3 again, it's the sample mean plus or minus T alpha over 2 with N minus 1. So this is a T critical value that we'll have to look up from a table times the sample standard deviation divided by the square root of N. So this is the appropriate formula for our confidence interval. So alpha is equal to 0.01, so alpha over 2 is 0.005, half of that. And then N minus 1 is going to be equal to 9, so we need the T 0.0059 value, okay? And we looked that up. That's actually going to become, we're going to look in table A.5 for that. So let me see if I can switch over, pull up that table really quickly. Table A5, our new parameter here is 9. Notice these are T alpha new values, and our value of alpha, it's really alpha over 2, is 0.05. So this is the 3.250 value that we're interested in. So switch back. So this is 3.0, I'm sorry, 3.250 from our table. And so that was the only unknown in this equation. So this is 2.6 plus or minus 3.250 times our sample standard deviation, which is 0.6, divided by the square root of 10, and then subtracting, I'm going to get the lower value for my confidence interval. That's 1.983, and then adding, I get 3.217. So this is relatively easy to do on your calculator and relatively quick, especially if your calculator allows you to recall the previous entry. So just enter this line to get the lower limit, and then recall it and change the minus to a plus to get the upper limit. Okay, and so this is the 99% confidence interval for this particular problem, part A. Oops, let me switch back over to the exam. Part B, find the tolerance interval that captures 90% of the population with a confidence level of 95%. So in the previous, in part A, we were only interested in capturing the mean. Now we want to come up with a level that captures 90% of the population, or an interval that captures 90% of the population with 95% confidence. So this is going to be a larger interval than the one that just captures the mean. So part B here, the relevant formula is the tolerance interval is equal to, and the sample mean plus or minus, now these tolerance critical values times the standard deviation. And these tolerance critical values are in table 8.6, and let me refer back to, so we want 90% of the population, 95% confidence. We need both those values to actually get the right tolerance critical value out of this table. So now let me pull up that table. Confidence level 95%, 90% of the population, and then this is actually the sample size, not 1 minus the sample size, but the sample size. So our sample size is 10 for 90% of the population, 95% confidence. So this is the value we want, 2.839. Okay, is that tolerance critical value. So going back to the whiteboard, from this table, we've got this tolerance critical value is, what did I say, 2.839. Okay, and then so now the tolerance interval again is my sample mean, 2.6, plus or minus this 2.839, and then times the sample standard deviation of 0.6. Okay, doing that calculation, I get for the tolerance interval 0.8966 for the lower limit, and 4.3034 for the upper limit. Okay, that brings us to part C, where we're asked to calculate an upper confidence bound, not a confidence interval, with a confidence level of 95% for the standard deviation. Okay, so again, that may have been another section in the textbook in chapter 7, but here the upper bound, this is actually on sigma squared, is given by this. It's n minus 1 times the sample variance times a chi-squared critical value. And for the upper bound, it's chi-squared 1 minus alpha n minus 1. Okay, and let's see again. in the problem here, 95% confidence. So alpha is actually 0.05. Now, if you look at the formula for, I think the confidence interval, it involves 1 minus alpha over 2, and then an alpha over 2 value for the other limit. But if you read the print right below, it says if you're calculating one-sided bounds, use alpha, not alpha over 2. So you use alpha over 2 critical values when you're calculating a confidence interval. But if you're calculating just upper or lower bounds, use alpha instead of alpha over 2. So we're interested in chi-squared. 1 minus alpha is going to be 0.95, and then n minus 1 is equal to n. So these are in table A7. So I think I've got that here as well. So here are alpha values across the top. We want the 0.95 case and then n equal to 9. So that's a 3.325 value from this table. So going back, this is, what did I say, 3.325, and then plugging in for this upper bound, n minus 1 is 9. The sample variance is the sample standard deviation squared, and then divided by this particular chi-squared critical value, and plugging in, I get an upper bound on the variance of 9.744. We were actually asked to, it wasn't the variance, right? It was the standard deviation. So this is an upper bound on the variance. The actual upper bound we're interested in is the upper bound on the standard deviation. So we need to take the square root of that. Let me pull away here so I can grab a calculator. Square root of 0.9744 is 0.9871. Okay, for the answer to part C there.